In this section, we're gonna start introducing the concept of F net, Newton's laws, first law and second law. Remember, we discussed the concept of equilibrium. What does it mean? It means that equal this way, I am here. Equal up, equal down, right? I am staying put. Equilibrium means, in essence, that this thing is floating as is, and the forces acting on it keep it still, stationary, no movement, okay? That's what we're looking at for equilibrium. And remember, what we did is we worked out the resultant. We added the forces together, either using the graphical method or using the algebraic method. And we did some examples. Now, if you remember, we were talking about components. Let's just quickly recap on that element. We had a force, and it was 100 newtons, and we had it acting at an angle up there, 100 newtons. Remember, draw these things, right? That's the only way forward with it. So we've got 100 newtons. Then I said, okay, dokie, what is remember we split this into the horizontal, Fx, and Fy, the vertical component. We then said, let this be 45 degrees over here. Now, Fy, the vertical component, you could use Fv and Fh if you like. Okay, horizontal, vertical, right? So all we've got to do is split it into components. How much is pulling up and how much is pulling to the right or to the left? How do we do that? Well, we stand inside the angle here and we look out and we find opposite, which means sine. All right? That's what we do. Remember, it's always wise to just stand in the angle and find opposite as the sine, because if this changes direction, it can be pointing downwards or at angles and things like that. So we say that is going to be 100 times the sine of 45 degrees. This is going to be 100 times the cos of 45 degrees. Okie dokes, which is great. Now we can go ahead and we can work that out. I've already done it. It comes to 70.7 newtons, and those bright ones amongst you, the other one, 70.7 as well, isn't it? Why? Because it's an isosceles triangle 45-45. So our component up and there are the same, there and there. Okay. Now, can you see, as I move this up, let's say I make it 100 newtons again. Now on this side, look what's happened. As it moves up, so this one gets shorter, doesn't it? Here, my horizontal gets shorter. When it's right at the top, I've got no horizontal component. In other words, it's pure, back to our soap on the rope, it's pure lift. You can see it. There we go, like that, right? Part of it is the up and part of it is the horizontal. It's got the components, right? So if we do that at 60 degrees as an example, all right, we end up with over here 86.6. And over there we end up with 50 newtons. So as I am moving up, let's use a triangle. Let's use one of these set squares, shall we? Okay. And as usual, when you want something, it's never there, is it? But okay, let's just use this over here. Okay. Here you can see, right? That is my 100 newtons, isn't it? Right? There it is. Now, what is happening? Look, as it's there, it's got the full length. But as it rotates up, my horizontal component becomes 0, right? So in these situations here, there's a little element of practicality to just look at and say, yeah, it looks about right. It should be, that should be less than that one. If it's not, then obviously you've just used the sine and the cos the wrong way. You didn't look for opposite, did you? Okay, always remember, look for opposite. It works. Okay, so as we get steeper, okay, so the components are going to alter. And ditto, as we get less steep, it's going to become more and more until it's a pure pull to the right or to the left. So now, therefore, as the resultant moves, right, because if there's a resultant, what does it mean? It means that it's unbalanced, okay, isn't it? A resultant A resultant means unbalanced. Object or body will move. Remember we spoke about sitting and moving, ducking for a door or whatever the case might be. This element here, we're now introducing the fact that, well, what if it's not in equilibrium? Well, we go back to our proverbial soap on a rope. We say, all right, that's in equilibrium, isn't it? This is down and I am holding it up, right? And I am balancing out the weight. I am in equilibrium with the weight of this, aren't I? Right? Now, let's just think for a second about this. Well, we've got to now start looking at out of equilibrium. Remember, what was the resultant? What was it? Let's just recap. The resultant is the result of all forces acting. So it's the single force taking the place of all others, right? Okay, it's the single force taking the place of all the others. That's what the resultant is. Okay, now, what is the next step I have to do? The next step is, remember that when we worked out the resultant, you get a whole lot of forces like that and down here and maybe one up there. Remember, we put them all into components, positive, negative, take the positives, subtract the negatives, and find the final. Gives us, let's say, for example, it gives us a force that way and a force that way like that. And then we went and we worked out the final resultant force, which was, say, over there, R. And remember, it was the square root of Fy squared plus Fx squared. And we worked out the angle, which was theta's arctan of Fy over Fx. Remember those? Okay, just to recap those. Now, when we found the single force that represents all of the others, what are we able to do at that point? Well, we're able to say that this body, this thing, has got a resultant force of so many newtons acting in that direction. What does that mean? It means the body, this soap on a rope, is going to go in that direction, isn't it? Okay, just logically think about it, right? That's what's going to happen. It's going to move the way the force pulls it, obviously. So, I am on black. So now let's just consider this, because now we have got the resultant has got a magnitude plus a direction. Magnitude was how much plus, remember, which way, okay? Which way was it going? Okay, so we've got our magnitude and direction on this. Let's have a look now. Now, I apologize most profusely for the pain that you have to endure with regard to these. But yes, and I know I've said it before, but Newton's laws, all the laws, you have to actually be able to repeat them, okay? I'm going to sort of go through them here, and I'm going to unpack them. Then we're going to do some examples, how they're used, right? But let's understand them. But as I say, please learn them. Coulomb's law, Ohm's law, Newton's law, law of conservation of mass, law of conservation of energy. You have to know them. You have to state them. The law of conservation of momentum coming up. You have to know it, okay? That you have to do, okay? Now, let's just look at Newton's first law, okay? I'm not going to sort of whatever it, but in your books you will have it. Take it out, learn it, okay. It says an object continues in a state of rest or uniform constant velocity. So let's just unpack a couple of terms here, Okay, we got a body, something, an object continues a state of rest, okay, rest, or uniform constant velocity. Okay, unless acted upon by an unbalanced net or resultant force. Like so. Unbalanced net or resultant force. Right, let's unpack it. Let's use an example. Here we go. Sorry about that. Okay, there we go. Our box. Okay, and we're going to use these a lot. Okay, right. No, the ribbon's not my idea, but there you go. But now, that box is at rest. If something's at rest, it means no velocity. Correct? It's not moving. So it's going to stay at rest. And no matter what we do with the force or whatever we want to do, the box ain't going to move. It's going to stay put. Okay? But if something comes along externally, and there it is, there's a force external moving it, right? Why is it unbalanced? Well, because currently in the situation it's not there. Force is here. Boom. Okay, it pushes it out of the way like that. So there's an external force. Similarly, if you're on your bicycle traveling down a nice straight road, as long as you keep pedaling at the same rate, okay, or you're on your scooter, being in this grade of education, you are carrying along on a straight road, and you've got your accelerator, aka your pedals are going around, right, for a bicycle analogy, and then what happens is you get hit by a tailwind, or you get hit by a headwind, or you apply the brakes. Okay, those are all forces that weren't there before. They are now acting on the body. They are going to change what it's doing. Just think about it logically. That's all you have to do. A car, for example, our delivery truck over here, okay? Right? This thing, and I mean, seriously, playing with these things is a bonus for this, but this thing it's there. It's going, and it's traveling at constant velocity, right? I know it goes off screen, but let's just do it this way. Constant velocity until I put my foot on the gas, which means it's then going to accelerate. Yes, we're heading to acceleration now. That's where we're going. So now let's examine it. It says at rest, okay? For it to move, we have to apply a force. Okay, what kind of forces? A push, or a pull, or have a look, a lift, okay? Or even forces that cause it to spin. Forces that twist, okay? When you open a jar, you twist. That's a different force. We don't do these. We do those later on. Okay? If you're doing A-levels, we'll do those when we get to that section. But what have we got here? We've got a force which is acting on something that is either moving with constant velocity or is at rest. So, once again, note the word here. Unbalanced, net, resultant. We're going to come back to those. Okay. Now let's look at Newton's second law. Newton's second law, it says, if there is a resultant or net force, this is his first. Quite a clever dude, this. Second law, they say here, if there is a resultant or net force, so hang on, resultant or net force acting on a body or an object, the body will accelerate. Okay, here's a new one. Accelerate in the direction of the net or resultant. Okay, and the acceleration is directly proportional to the force. Acceleration is proportional to F, and indirectly and inversely to the mass, leaving us with F net equals ma. How do they get those others for those who want to know? A is equal to F over m, which means A is directly proportional to F, and A is proportional to 1 over the mass. That's where that comes from. Okay. Right, now, let's just unpack this just for a quick session with logic, okay? Let's unpack this and look at the logic of it, okay? What do we do? Well, it says, okay, as an example, right? Let's say we've got this, okay, our lift, right? Now, currently, it's hanging. Sorry, I just want to get it so that it doesn't, it's hanging up like that, right? There we go. Now, it is in equilibrium. It is not moving, right? Now, or if it's moving at a constant velocity, and we'll go through that example in a little bit. What are we saying here? We're saying that if there's a resultant or a net force, it means that now I have got that force R, right? So we've got our body with a force R acting that way, resultant, right? It says that the body or the object will accelerate in the direction of the force. Yeah, we said that a long time ago, okay? We said that this is going to go off in the direction that you pull it. We know this because if I want to lift this up, I have to exert a force upwards for it to move. Okay, I know I'm belaboring a point, but when you're looking at these problems, no, you can't just bang it into an equation and get an answer. You have to actually say, what am I doing? What is happening here? Okay, that is why I alluded to the thing that we're going to have to do is a little bit of logic. Because no, it's not just, hey, there you go. There's the numbers, there's a formula, plug them in. You have to think them through. So let's just look at an example, right? Let us say we are on a bicycle, shall we? And for my followers of art, okay, there we go. And whatever, that's pretty horrible, but hey, will do for me. Let's say I am moving that way on my bicycle, and I am pedaling normally on the bicycle, or aka also a scooter, by the way, it could be, got the gas down, and we're cruising along. The engine is exerting a force. What am I doing as I am pedaling? I am exerting a force, okay? If you don't believe me, then you take the person's temperature. You'll see they're starting to perspire because they are actually doing work. They're exerting a force, okay? If you remember back, work is force times distance, but never mind. You're exerting a force on the pedals going around. As long as that force stays constant, right? I am exerting a force that way, and the force this way is my force of friction. We're going to get to all of these, all right? So what am I doing? I am basically balancing out the forces, and I am moving at constant velocity. Constant velocity. Okay? So constant velocity like that. Okay. Now, let's think. What happens if I increase the force? Remember we said, there's my force, there's my friction. Okay? What happens if I increase the force? I've got an unbalanced force now. Isn't that so? Because friction is staying constant. It's not increasing because frictional force is mu times Fn. We're going to get through all these just now. Okay? But that stays constant, okay? Because F normal is mg. Okay? Now, what is happening here is that I've got an unbalanced force. Remember? Unbalanced force, resultant, F net, same thing. Okay? For what we're talking about now, okay, F net is my net force, or unbalanced force, okay? They are the same thing. So the key to all of these in any problem where we've got the possibility of acceleration is the key, find F net. Unless, of course, you're given it, right, and asked to go backwards. But that's not a train smash either. Now, let's just quickly consider something. If I am going this way, right, we are going this way in our car, right? and we put our foot on the accelerator or on your bike, right? We accelerate that way. Well, that's great. My velocity is going to increase, isn't it? Because I'm trying to overtake, right? So I have to increase the force, which means I have to increase my velocity. I'm accelerating, all right? If you remember Newton's laws of motion, right, from previously, what have we got here? But now what happens if I put the brakes on? I am decelerating. So my acceleration can be positive if it's in the same direction. Which means what? Go faster. Right? Or my acceleration can be negative if it's in the opposite direction. Which means I slow down. Okay? That's what that's about. Okay, cool. Let's put on another page there. Go back to the black. So what we've got here is we've got a situation where we've got these bodies that are going to accelerate because of resultant forces. So the first question is we look at the resultant force acting. Let's consider a lift problem. Let's just look at lifts. All right. Well, let's take our lift over here, and I'm going to actually do a numerical example. Step 1 is always what? Put in FG. Step 1 in all your problems. Okay? Put in FG or FW, the weight. Okay? Put that in straight away. Always put it in. Okay? Calculate it. And we say that FW is equal to M times G, which is going to be 9.8 times M, is it not? Okay, now we've put that in. Now what's holding the lift up? Okay, there must be a cable. If any of you have ever looked at a lift in a shopping center, especially the newer ones, they're glass and you can see the weights and everything moving. It's worth looking at it because it helps a heck of a lot with these problems, okay? So, you know what, I'd say, you know what, go to the mall, have a coffee or whatever, and go check out some lifts. Okay. The lift is now stationary. Let us say it's stationary or at rest. Please watch the wording. Okay. Stationary or at rest. I have got a tension in that cable, haven't I? Remember, cables can only hold a tension. They can't hold a compression. Remember when we played with this guy? All right. He can't hold a compression, he only holds a tension. Okay, what am I going to do now? Now I'm going to say, okay, let's say the mass of the lift is equal to 1,000 kilograms, so therefore that is 9,800 newtons. Now if it's at rest, what is, just put it here, T is equal to mg. What does that mean? It means that T must be equal to 9,800 newtons. Straightforward, simple, because it's at rest. I'm going to just put in here, okay, or at constant velocity, because that's what Newton said, okay, essentially, didn't he? Let's now consider the case, same lift, guys, the same lift. I'm putting in, here's my 9,800 newtons. This is FW. Now, there's my T. Say T is greater than mg. Say T equals, what did I say in my calcs over here? I think I said 10,000. Yeah, I did. 10,000 newtons, aka 10 kilonewtons, right? Please remember, very often it's given as kilonewtons, 10,000 newtons. Now, what's going to happen? Forget the physics and the algebra and everything and the maths. If the force up is bigger than the force down, the lift is going to move up. That's how it works, isn't it? Because the force pulling me up is bigger than the force down. And seriously, that's all you have to look for in this. Building up the sense of logic. In other words, when you're doing these problems, don't just bang in a formula. Look at actually what's happening. Because when you come to mid-years and finals and next year and A-levels, etc., and uni, you are expected to analyze it, not just bang it into a formula. Okay, when it's coming to bang into a formula, I'll tell you, believe me. Right, what do we do here now? Well, force up is bigger than force down. Is there a net force? Unbalanced force up. Net force up. Correct? Resultant is up. And how much? So we say F net is equal to up minus down, or down minus up. Doesn't matter. We'll get to the signs in a bit. F net is going to be equal to 10,000 minus 9,800, which is going to be equal to 200 newtons. Now, the moment you calculate it, or the moment you see an F net, the next thing is you say F net equals MA. Straight away. Okay, without even thinking about it. So I go and I say it's equal to MA, and I can calculate. Do I know F net is 200? Yes. Do I know MA? Yes, I do. The mass is 1,000 times A. Therefore, I am going to accelerate at 0.2 meters per second squared up. Therefore, we have to give it a direction, which is up. Okay? Remember, the direction is important. You want to know if you're in a lift, are you going up, you're going down, don't you? Okay? So the direction is important. So we've worked that out. What's the next step? Oh, yeah, obviously. What happens? Here we've got again, FW is equal to 9,800 newtons. Here I'm going to do the case T is less than mg or less than FW, whichever way you want to think about it, okay? So I say T is equal to 9,000, let's have a look, 9,800, okay? 9,500, okay? Now it's less. What happens? Well, obviously, if I can't hold it up enough, if the weight's too much, it's going to drop. That's all this is. That's all it's saying is you can't hold it. The weight's going to drop. So what do I say? I say, is there an F net? Question. Is there an F net? Okay. In this case, yes. I say, okay, why? Because down greater than up. Oops, spelled that with two P's, which was not cool. But come on. Okay. Yes, okay, down is bigger than up, so our net is down. So let's have a look. F net is equal to 9,800 minus 9,500, which is equal to 300 newtons, like so. Okay? Now, what is the trigger? The trigger is the moment I see F net, this guy here, I'm going to highlight it in red, that guy, I straight away say F net equals MA. Okay, no matter where you are, what you're doing, that you should be able to, the moment you wake up at 2 a.m., you should be able to say F net MA. I put in, what do I know? 300 equals 1,000 A. A is 0.3 meters per second squared, vertically downwards. Right? Very straightforward. Predicated on actually just having a little bit of the logic and asking what's going to happen. The next step, the last bit, is constant velocity. Constant velocity. What do I do here? Well, let's take our same lift. Okay, there she is, like so. And I say this, my FW is equal to 9,800. Right, now I want to know what is T. Let's reverse logic this. Constant velocity means what? It means V final is equal to V initial. Acceleration is 0. There is no acceleration. Acceleration, I write down straight away. F net equals ma. Acceleration is 0, so my F net is equal to mass times 0. So F net equals 0. Okay, I know this is long-winded, but can you see the logic here? If F net is 0, it means no unbalanced force, and it means no resultant. Therefore, force up must equal force down. Okay. Therefore, T must equal 9,800 newtons. And that is it. What are we saying with these? And I know we carry on in the next ones, but what we're saying is that we're looking for F net. But you have to, and I've said it many times, with physics you have to draw it and become the block. Ask logically what is happening, right? How does it move? How does a lift work? Well, it's loaded with people, therefore I'm going to have to pull harder to get it to go up, aren't I? I'm going to have to accelerate it upwards. Use it with practical examples. A car, your bicycle, a scooter, whatever, a motorbike, right? You can see here that it's actually exceptionally logical. Okay? So thanks for watching that. And remember always that in the exam prep, test prep, okay, there are more questions. And as I've said, we're going to be loading a lot more into it as the site progresses, as it moves, as we get feedback on please do more of these problems or more of those problems. We're going to put them in. As people ask us to solve problems, we're going to put the answers onto video sessions for everybody. So please enjoy the next ones, and good luck with the endeavors. And always remember, draw it. Secondly, become it. Cheers. Bye.